So let's go ahead and do that anti-differentiation now. Incidentally, this latest break was once again due to the fact that it stopped recording audio. That was not a deliberate break on my part. So antiderivative of 1 over x is log absolute value x. For this dude, so according to the formula above, or you can do a u substitution if you want, we have log x squared plus 4 over 2. Right, and this is easy to verify on your own, because differentiate this guy, you get 1 over x squared plus 4 times 2x, so that 2 and this one half cancel, and we're good. And then as for this guy, that's that arctangent formula with a equal to 2. Like so. Okay, and that's all there is to it. Let me just double check that really quick. Okay, yeah, we're good. Yep, so that's all there is to that one. So the integration step on all of these problems really should be the easy part. The hard part is just getting the decomposition in the first place. Okay. So, notice in these formulas that I've posted up here, we have x squared plus a squared, ax squared plus b. In these denominators, we only have a square and a constant. We only have a square and a constant. However, quadratic factors in general might have a square term, a linear term, and a constant term. So, if you want to use these formulas up here, and yet you have been given a generic quadratic, then you might want to complete the square to put it into this form, where it's just a square and a constant. That way it will be more amenable to the formulas that I've written down. So here's an example where we're going to have to do something like that. Okay, so first off, compare the degrees. And, well, here the degree on the top and on the bottom, they are the same, so we are going to have to do polynomial division here. Okay, so n is equal to 4x squared minus 3x plus 2, and d is equal to 4x squared minus 4x plus 3. So let's go through it. All right, divide the leading term of n by the leading term of d. So 4x squared over 4x squared equals 1. And then that gets put into the quotient. Next, take the result of step 1 and multiply it by d. Well, okay. You're just getting the same thing then. Next, take the result of step 2 and subtract it from n. Like so. And this is going to become our new n. So let's see, 4x squared minus 4x squared, that cancels. Minus 3x plus 4x. So that's x. 2 minus 3. So that's negative 1. And then overwrite n with this. And now let's compare the degrees of n and d again. So the degree of n is 1, and the degree of d is 2. So, since the degree of n is now strictly less than the degree of d, we are done. And set r, the remainder, to be the current value of n. Okay, so far, we have done polynomial division to obtain the following result. So this is equal to q plus r over d. And now we're going to do partial fraction decomposition on this bit. Okay, so factor the denominator. So 4x squared minus 4x plus 3. Let's see. So, okay, circumstantial evidence would indicate that this guy is probably irreducible, right? Because this is already quadratic, and this case is all about having irreducible quadratic factors. So certainly we can't factor this guy without making its degree smaller, and thereby getting rid of its quadraticness. So circumstantial evidence would indicate that this guy is irreducible, and indeed we can prove this by showing that the discriminant is negative. So I should say factor the denominator if possible, but this guy is irreducible. So recall, a quadratic ax squared plus bx plus c is irreducible, cannot be factored without introducing imaginary numbers, if the discriminant b squared minus 4ac is negative. Right? Because in the quadratic formula, that's the bit that's underneath the square root. So if that guy is negative, then that means that the solutions are imaginary numbers. So in our case, we have b is equal to negative 4, a is equal to 4, c is equal to 3. So that is 16 minus 16 times 3. Yeah, which is indeed going to be negative. Okay, so yeah, so this guy is already fully reduced. There is no more to be done in terms of partial fractions. This is already in its partial fraction form. Indeed, notice that the numerator is linear. So yeah, the partial fractions have already been done. In this case, there's no more decomposition to be had. So now we just need to integrate this thing. Okay, so integrating this first guy, of course, is easy. That just becomes x. Integrating the second guy is not obvious. So this is the reason I brought up this idea of completing the square. Because if we can complete the square on this guy down here, we'll end up with getting something squared plus a constant. Then it will be more amenable to one of the formulas above. So let's complete the square on this dude. So let's see. To complete the square, basically you're just plugging in numbers in this formula here. So A is equal to 4, B is equal to negative 4, and then C is equal to 3. So we have 4, let's see, 4 over 4 cancels, so this is minus 1/2. Squared. Oh, that's weird. Why isn't there a squared here? So 16 over 4. Oh, this is just 16 over 16, so this is minus 1. Minus 1 plus 3 is plus 2. Okay, so there's that. So that is actually what we have in the denominator here. And once again, I'm going to go through the trick where I split this into 2 more pieces. So x over the denominator minus 1 over the denominator. So we have x over all of this junk minus 1 over all of this junk. Like so. Now this is tremendously ugly, but we can do this. Now this looks very close. This looks very close to this formula right here. Actually, wait, which one? Yeah, this formula right here. Well, 2 of them, this one and this one. It sure would be great, though, if we could replace that big ugly x minus 1/2 with just a single variable. So, well, let's go ahead and do that. Let's replace this x minus 1/2 with its own variable. And, in fact, let's do more than that, because 4, this is 2 squared. So let's include that as well. So let's let u equal 2 x minus 1/2. Right? Because then this bit here is going to be u squared. This bit here is going to be u squared. So that'll make things a lot nicer. So then, differentiate. So du is going to be just 2, right? Because derivative of this thing is 1. 1 times 2 is 2. And consequently, like so. Right. So then our integral becomes, so let's just anti-differentiate this 1 to get that taken care of. So we have x, but here's the thing. We want to write everything to be in terms of u, right? So let's take this equation here and solve it for x. In fact, yeah, let's do that. Yeah, let's do that first. Let's do that first, and then we can split it up into the 2 pieces. I feel like that might end up working out better. Yeah, so let's do the u substitution first, and then maybe we'll split it into 2 pieces if we need to. Okay, so let's solve for x here. So x is equal to u over 2 plus 1/2. So that is that. So in the numerator, we have x minus 1 like so. And in the denominator, we now have u squared plus 2. Okay, and then instead of dx, we're going to write 1/2 du. Okay, so now we're getting somewhere. Now this looks much easier. I mean, of course, it's still ugly, but, you know, what are you going to do? So this 1/2, let's pull that out front. Oops. Out front. And then as for this dude here, so we can simplify this into, I can replace this 1 with a 2 over 2, so that we get u plus 1 minus 2. Well, u plus 1 minus 2 is minus 1. And then this over 2 here, well, let's just pull that out front as well. This is just going to be another factor of 1/2 that we can pull out. To make that 1/4. Okay. And now we are in a position to split this up fully, to split this up more, because then we're going to end up getting something which is exactly the same as what I had in the formulas upstairs. So u over u squared plus 2 minus 1 over... And you know what? Let me distribute that 1/4 in there as well, just so that I can see that being a possible mistake. Okay. So now I have now split that into 2 pieces and distributed the 1/4. Okay, so now this is exactly like this dude up here, where a is equal to 1 and b is equal to 2. So may as well combine this into 1/8. And then as for this dude, well, this is exactly that arctangent formula. So 2 is the same as square root of 2 squared, right? Because a is the square root of whatever number is present here. So this is 1 over root 2 arctan u over root 2. Okay. And may as well write this in 1 fraction, like so. Okay, so last thing to do is to rewrite those u's to be back in terms of x's. So since u is equal to all that junk, well, yeah, it's ugly, but that's the only remaining step. And with the magic of copy and paste, it shouldn't be too painful. Okie dokie. So now we can wring our hands forever trying to get this into a much nicer looking format, but I don't know. All the hard work has been done at this point. Because like, so to be fair, what you would see in the book is probably more like what I'm about to do. For some reason, the book really goes through a lot of pains to put this into a particular form. So here's my anticipation of what the book would probably do with this. They would probably want you to square this 2 to make a 4. And when I say the book, I mean by extension the multiple choice responses in the homework. So they would probably want you to square this 4, and they would probably want you to FOIL out this x minus 1/2, so that we would get x squared minus x plus 1/4 plus 2. Usually he doesn't want you to rationalize the denominator, so at least there's that. But with this bit, he would probably want you to take this 2 and distribute it, which is not bad, because that means this 1/2 is going to get canceled. So 2x minus 1 over root 2. And then we can clean this up a little bit too by distributing this 4. So 4x squared minus 4 plus 1, and then plus 1 plus 2 is 3. And that is indeed the form that it's in the book. Yep. So that last bit, well, yeah. It is good practice at the very least to go through algebraic stuff like this to try to make it look as nice as possible. It's not a bad thing. Not strictly necessary, but not bad either. But yeah, these problems are long and are long and intensive enough as it is. Okay, so that's all for this one.